Okay, so today's notes we're trying to solve exponential or log equations, meaning that there is some variable, usually x, in there, and then we're trying to solve for the value of x that makes the statement true. So there's basically four different methods for solving these. The first two are very similar. It's either we're going to try to make the bases same in log form, or we're going to try to make the bases the same in exponential form. So if you look at number one, it's already in exponential form, and I notice that 4 is a base, 1/2 is a base. I can do a change of base on these to a common base, 2. So when I change the base on the left, it is now 2 squared raised to the x power, and 1/2 with base 2 is really 2 to the negative 1 power, and that's being raised to the x minus 3 power. Our power rule says that power raised to a power means multiplication. So now it's 2 to the 2x power equals 2 to the negative x plus 3 power. And then we have an equality property that says if your bases are the same, that must mean my powers have to be equal to each other. So now we have 2x equals negative x plus 3. And then you simply solve for x after that. And so I get back x equals 1. And then if you want to make sure your answer is good, you'd plug it back in just to make sure it makes sense. So 4 to the first power is 4. And then 1/2 raised to the 1 minus 3 is like saying 1/2 raised to the negative 2, and which also equals 4. So 4 equals 4, true statement. We solved correctly. All right, then on number 2, I have exponential form on both sides. And I notice that I can rewrite 9 and 27 in base 3. So that would be 3 squared to be 9, and it's raised to the 2x power, and 3 cubed raised to the x minus 1 power. Power rule says power raised to another power is multiplication, so you have 4x equals 3x minus 3. Because my bases are the same, means the powers must be equal to each other. And you solve for x. Okay, so those are some examples of where I can change the base in exponential form. If we flip over to the back, we can see that when I have some log problems, I need to have log on both sides. If my bases are the same, that means my arguments have to be equal to each other. And if you think about rewriting this in exponential form, that makes sense, right? Because they both have the same base. To some question mark gives me the answer of 4x minus 7 on both of them. The arguments are really the answers, right? So that means your arguments have to be the same. And then you simply solve for x. Okay, there is one extra step that you have to do if your original problem is a log function. You have to think back to your log function, the way it's graphed. We have a restricted domain on it, right? We have an asymptote, vertical asymptote here at x equals 0, and then my function looks like that. So that means I cannot perform log on any argument that is from negative infinity to 0. So we have a restricted domain, right? I can only complete log functions on arguments that are from 0 to infinity. So when you solve for x, and x is part of the argument of a log function, you have to check for extraneous solutions, meaning when I substitute my x value into the argument, is it going to conflict with my restricted domain? So basically what we don't want to happen is to have an argument come back as 0 or negative. So when I substitute 4 in on this side, I get 16 minus 7. So we're good there. And when I substitute 4 on the right side, I have 9, which is still good. So this is a valid solution. And what we don't want to happen, what would make it extraneous or a false solution, is if your argument is outside of your restricted domain, meaning negative infinity to 0. So if your argument is this, then you have a false solution. All right, so that covers what to do if you can find a common base in either exponential form or log form. So those are our first two methods. If that's not the case, right, what should we do next? So looking at example 3, I'm in exponential form, and I notice that my base 4 and my base 11 over here have no common smaller base that I can rewrite these in. So that means I can't rewrite them in exponential form with a common base, but I could rewrite them in log form with a common base if I take log base 10 on each side. So I'm going to do log function base 10 on each side. And remember, you don't have to write the base 10. If you leave that off, mathematicians know that we're talking about common base 10. So I do log on each side, and now these are arguments. 4x is an argument, 11 is an argument. Sorry, this is 4 to the x. 4 to the x is an argument. All right, so that helps us because I have log rules that can remove x from being a power. We have a log property that says if I rewrite this in expanded form, this is really like a multiplication, right? So now this is x log 4 equals log 11. And now x is almost by itself, right? This is a product here. Log 4 is just a number. Log 11 is just a number. So to get x by itself, I need to divide by log 4. So my exact answer is x is equal to log 11 divided by log of 4. On a quiz or test that wanted a rounded or estimated answer, you could actually do this in the calculator, have the calculator compute it because it does already understand log in base 10, and you would get 1.730. Okay, so for example 4, again, I notice I'm in exponential form and I cannot rewrite the bases in some common base. So what I'm going to do is perform log function on both sides of my equation. So now they do have a common base for log, right? And then I'm going to use my log rules to notice that the power of the argument is really a multiplier to the function. So 9x times log 7 equals log 15. Log 7 is a number, log 15 is a number, right? 9 is a number. I'm trying to isolate x, so first I'm going to divide by log 7. So then I have 9x equals log 15 over log of 7. And then to get x by itself, I just need to divide by 9, divide by 9. So an exact answer would be log of 15 divided by log of 7, quantity divided by 9. And if you had to estimate this answer, then it would be 0.155. Okay, so on my next example, so on the next example we have an equation with e in it. Remember, e has an inverse, it's the natural log. So we're going to end up taking the log of both sides, but this natural log on both sides so that it will cancel out with this e. But before I can do all of that, I kind of have to isolate it first. So you're going to do a plus 7 on both sides first, and then we have 4e to the negative 0.3x, and then to get e by itself, we have to divide by 4. So then I have e to the negative 0.3x equals 5. Now that e is isolated, now I can take the natural log on both sides. Remember, those are inverses of each other. It equals 1. So now I have negative 0.3x equals the natural log of 5. And then to get x by itself, I just need to divide by negative 0.3. So x exact answer is the natural log of 5 divided by negative 0.3, or an approximate answer from the calculator would give back negative 5.365. Okay, so far we have solved by making the base the same in either exponent form or log form. These last examples that we worked out was solving by taking the log on each side. So the only other thing we have to cover is what if your equation already has log, but it's not a log function on both sides of the equation. So what do you do in situations like that? So it can look like this, where there is just one log expression equal to some number, or we can have something like this where I have a combination of log function equal to something that's not a log function on this side. So in both these situations, the rule is always to condense. We want just one log function on one side of the equation. And so example 7 is already like that. If you can get it to this point, we can always solve by rewriting in exponential form. So exponential form has the same base as log, and then the answer over here is really the power, and the argument is the answer in exponent form. So we can rewrite it in exponent form to be 4 to the third equals 5x minus 1. 4 to the third is 64, and now it looks real normal, like we can solve this without any problems. Okay, we need to remember that my original problem had an argument with x in it, which means you have to check your solution. So if I substitute 13 here, does that cause any negative values or 0? And 5 times 13 minus 1 is not negative or 0, so that this is a valid solution. On number 8, we're going to use the same method, except for I have to consolidate and condense this first into one log expression. So we have rules, log property rules, that says when you're adding two log functions, really you're multiplying the arguments. So this is log of 8x times x minus 20. You're going to distribute and get log of 8x squared minus 160x. Okay, now that I have it all as one log expression on one side, we can rewrite this in exponential form. And let's not forget that if there's no base for log, it's really base 10. So this is 10 to the third equals 8x squared minus 160x. We're going to move that over there because this is a quadratic. And we solve quadratics by setting it equal to 0. We're going to take out the GCF of 8. And divide by 8 on both sides. Then we're going to find the factors of negative 125 and add up to that, negative 20. So x can be 25 or x can be negative 5. Again, we have x in the argument, so we're going to have to substitute the values in to see what happens. We don't have a problem with 25 because I still end up positive on both those, so that's a good solution. But when I substitute negative 5 in, I get back a negative argument, and we cannot perform the log function on negative arguments. So that is not a valid solution, extraneous. And so I have one solution, x equals 25.